For high school students, simple laboratory experiments bring science to life. This particular experiment is also of great interest to professional scientists looking for solutions to the world's energy crisis. The jar is collecting bubbles of hydrogen. It comes from ordinary water through which a small electric current is being passed.
I think it's about finished now.
Yeah. Let's get this hydrogen.
The collected hydrogen can be combined again with oxygen to produce water and a vast amount of energy.
Like the match. Look out.
The same reaction is used to power the American space shuttle. Faced by the threat of dwindling oil resources, research teams all over the world have been trying to harness this unruly energy to the more mundane task of powering the family car. This car, developed at Melbourne University's Department of Mechanical Engineering, is encouraging evidence that it can be done. It runs on hydrogen instead of petrol, in a modified version of an ordinary internal combustion engine. These modifications have taken 15 years to develop in a long-term research program led by Dr. Harry Watson and Eric Milkins. Dr. Harry Watson.
This car, running as it is now on gas cylinders, has a range only of about 40 kilometres. But with a hydride tank installed, we will expect a range of about 200 kilometres. Loaded as we are now to the same weight as though we had the hydride tank, we have made 3 significant discoveries. The car will keep up with the traffic even under freeway conditions. The pollution levels from the car are very low, compliant with the most stringent standards existing in the United States or Japan. And lastly, and most significantly, the energy consumption of the car is such that it will go 70% further on the same amount of energy as though it were running on petrol.
Although the car can be driven around the streets like any other vehicle, at least on short journeys, it spends most of its life anchored to a dynamometer, subject to rigorous scientific scrutiny. The researchers are particularly interested in testing the car's exhaust emission under various loads and comparing the results with those of a conventional petrol engine.
Right, now Chris, can you plot those results, please? Oh, Harry, these are some results of the petrol car and the hydrogen one. Lots of emissions, hydrocarbons, CO, NOx with petrol, and only a little bit of oxides of nitrogen with the hydrogen.
Each design modification is carefully tested. So far, the results have revealed that the car actually performs better in some ways on hydrogen. It's more efficient by about 40% and produces fewer pollutants. There are no carbon gases, some oxides of nitrogen, and hydrogen dioxide, otherwise known as water, pure enough to drink. Using a bench rig, Eric Milkins demonstrates the most serious problem they've had to face.
Well, that's the backfire problem in a research engine, and we can't have that in a motor car. This is a cutaway section of a cylinder head, and this is the special valve we've developed to control that backfire problem. The valve allows air in before the hydrogen, and so cools the charge. Also, we have to have special coatings inside the cylinder. We have to have special lubricants. Finally, under some high load conditions, we have to resort to water injection.
Eventually, the modifications will be controlled electronically, but for the moment, the systems are mechanical. The inlet system has been modified to replace the carburetor. The distributor now rotates as the vehicle accelerates, while controlling the gas flow sets the engine speed. In these experiments, hydrogen is stored under pressure in large cylinders. This is where, compared with petrol, hydrogen performs very badly. Despite their size and weight, these cylinders contain only enough gas to drive the car for 40 kilometres. This problem is being tackled by Dr. Douglas Bradhurst and his team at CSIRO's Division of Energy Chemistry in Sydney. They are experimenting with a metal hydride storage system, a radiator-sized arrangement of pipes filled with as much gas as a conventional cylinder, but at lower pressure. Using a test rig based on a small rotary engine without a carburetor, they're able to compare the two storage systems. They have to make sure it's possible to extract the gas from the new system smoothly and fast enough to supply the engine. The storage pipes are actually solid. They're packed with a powdered metallic alloy of iron and titanium. Under slight pressure, the hydrogen will bond chemically to the alloy structure, forming a metallic hydride. A whole family of alloys has been developed with this useful trick. Each one performs best at a unique combination of temperature and pressure. Their absorption characteristics are tested in collaboration with Dr. Watson's project at Melbourne University as part of a program to develop new alloys with greater storage capacity. In searching for ways to produce hydrogen from water efficiently and economically, a number of new approaches are being tried. At CSIRO's Division of Applied Organic Chemistry in Melbourne, Dr. Wolf Sassy and his team have been investigating how a special ruthenium dye responds to light. The dye reacts photochemically to break down the water molecules and produce hydrogen using light rather than electricity. The idea behind Dr. Sassy's work is to use the energy of sunlight to power this hydrogen-producing reaction.
The experiment you just saw is, in a sense, very efficient. In fact, it's 10 times more efficient than what most of our competitors overseas can do. On the other hand, we still have to solve the problem of stability. We have to produce components which last longer so that these compounds don't have to be renewed too often. The ultimate picture that we have in our minds is that of a shallow lake or pond which will be sitting in the sun, slowly producing hydrogen day in, day out, whether the sun is shining or not. And this picture is something which is in the mind of many people in this country and overseas. Whether it can be realized will depend, of course, on the success of our work and the work of other people.
This intriguing machine is a cross between a photovoltaic cell and a solar water heater. It's a completely different approach being tried by Dr. Bradhurst in Sydney. He's interested in adapting these existing technologies in order to generate hydrogen. The curved reflector focuses sunlight onto a central tube containing a pair of electrodes. One is made of titanium with a coating of titanium oxide. This functions as a semi-conducting layer to absorb light and generate bubbles of gas. The economics of the approach are very promising. The problem is to scale it up and increase the efficiency.
This collector demonstrates that hydrogen fuel can be produced from solar energy, either for domestic use or as a vehicle fuel. We have designed a flat plate collector, rather like a domestic solar water heater, but the amount of hydrogen you would get from something like that would only fuel your car for half a kilometre. So our laboratory research is aimed primarily at improving this efficiency up to the point where useful amounts of hydrogen are produced. The whole beauty of hydrogen is that it has 3 times the energy per unit weight of gasoline.
This technology could have a spectacular effect, not only on the car, but the home of the future. It's possible that domestic solar collectors containing semiconductor electrodes could heat the domestic water supply as well as providing enough hydrogen to power the family car. These preliminary experiments point towards a whole family of new technologies. They're part of the motorist's secret dream, to run a car on nature's unmetered gifts: sunlight, air, and water.